Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar session on water quality in the distribution system. My name is Zoe Eisel from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application? Falling short on project funding? Not sure where to start? EFCN is here to help. Use the link in the chat to submit a request and receive tailored support based on your project's needs. And on that note, we can get started. I would like to introduce our presenter for the day, Daryl Gotham, Senior Research Engineer at the Great Lakes Environmental Infrastructure Center. Welcome, Daryl, and I will go ahead and hand it over to you.
All right. Thank you, Zoe. As we get this set up here, hopefully it works.
Let's see.
We're having a little trouble. You can see it?
Yeah, I don't think it's the first page, but I can see it.
Yeah, okay. So, all right, well, thank you all. We'll briefly go through some of the things we're going to talk about here. We've got an overview of the topic, which is very brief. We'll discuss flushing of a distribution system. We'll talk about cross-connection control programs. We'll discuss disinfection, and then a small piece on monitoring. This is a course that's been condensed down. We typically give this course over it's a 2-day, 2.5 hour a day, 5-hour total training. And if you're interested in that, we are giving this the 5-hour training on January 6th and 7th. And I believe that Zoe will be putting that in the chat so that you can all check that out if that's something you're interested in. A link to that is. The first thing is scope of our discussion. So we're going to talk about the distribution system. There's a lot of different components that make up water treatment system and distribution system. As you can see, we've got the source, we've got the treatment, but we're going to concentrate on our stuff that's after the entry point to the distribution system. So it's going to be everything to the right of that point. We've got storage. With storage, we can see increased water age and nitrification. We potentially have dead ends. Ideally, we don't have these, but if we do, then we can see concerns with disinfection, byproducts, and loss of disinfection residual. Our pipes can contribute to bacterial growth, corrosion. We can have leaching and/or permeation from the pipes. And then finally, we've got cross connections, and cross connections are potential sources of contamination entering the system, whether it's through backflow or back siphonage. So we have a source water, and that source water quality can also affect things in the distribution system. Things like pH and alkalinity changes, if we change our disinfection, or if we change any of the treatment that we're utilizing at the treatment plant. So the first topic we're going to talk about is water age management, and what are some of the practices that we can do? One of the management practices that can help with water age. So we can make sure that we have sufficient turnover in our tanks that are out in the distribution system. We can flush and preferably eliminate any dead ends that are out there. So the figure at the top right shows the effect that that we can have with time on chlorine residuals. As we see, the chlorine residual, it drops as we go through time, and then our THMs will increase through time. So the time that, and so some of the factors associated with increased water age, as we said, loss of disinfection residual, increased microbial activity, so we can have growth out there in the distribution system. We'll talk a lot about disinfection byproducts. We can form those in the distribution system with increased water age. The potential to have corrosion on the inside of our pipes and tuberculation, and then also the potential for nitrification in the tanks and in dead ends. Here's a link to a study. There'll be several of these links throughout the presentation, and hopefully you'll get a chance, you can look at those and they'll find those useful. So dead ends are not a good thing, and we show this this little fake water system is full of dead ends. This would be a horrible system to have to maintain. So these are the dead ends, the points that if the water main doesn't loop back to itself, then that's a dead end. In this instance, about the only loop that we have is up here in the system. So dead ends are not good. So the study from 1996 found that distribution systems that have dead ends with free chlorine residuals less than 0.2 parts per million had substantially more occurrences of coliform system-wide than systems that have higher residuals. So that's telling us that we need to keep those residuals up to avoid having those coliform occurrences. I had mentioned storage tank turnover, and storage tank turnover is the time that it takes for the water to go through the tank, from when that molecule enters until that same molecule leaves the tank. Ideally for best performance, we want to have that turnover be less than 5 days. So we're not keeping that water in the tank for extended periods of time. One thing that this training doesn't have that the 5-hour has is a lot of math, and this is probably the only math problem we'll do, but as an example, we have a 500,000 gallon storage tank, and it receives an average flow of 175,000 gallons a day. We want to calculate the turnover in the tank in days. So there's our tank, and it signifies the flow. So first thing that we would do is we would convert that 500,000 gallons into just straight gallons. We do that by multiplying by 1,000,000 gallons, and that tells us that there's 500,000 gallons in that tank. And then we need to divide that volume of 500,000 gallons by the flow. So that's simply our 500,000 gallons divided by 175,000 gallons per day, and that gives us a turnover of 2.86 days, which is considerably less than our 5 days, so that's a good thing. Now with our tanks, another issue that we can have is short circuiting. So it's the idea that the water that enters isn't necessarily could be the first water that exits. So what we want to do is we can see in this animation that we're putting water in at our inlet that's cold. This is pretty common. And the way this tank is stratified, we've got lighter, hotter air or water at the top, and we've got cooler, heavier water at the bottom. So when we put that cool water in, it's going to drop to the bottom, and it's going to escape our tank. It's going to hit our outlet prematurely. So this can be a problem. So what would happen is this warmer, lighter water is going to stay in the tank longer and potentially cause us some problems. There's ways we can fix that. So here's an example of a propeller type mixer. So there's a propeller inside the tank that just causes that water to move around and circulate. Here's an aeration or a bubbler style, and that is going to force air up, which is going to cause the water to move around, and it'll all make it more of an evenly distributed old and new water. And that can reduce, the extreme differences in water age, and one of the key things to limit that disinfection byproduct production. So we've got some water quality benefits of system flushing. So flushing our system can help out with several different things. It's going to reduce our water age. So we're going to put new fresh water in because we're pulling the old water out. We're also going to freshen up our chlorine, and we'll have better chlorine residuals because we're putting fresh water in there. With that, with both the chlorine and the water moving through the system, we're going to reduce the growth of microbes. We'll also pull out any sediment that's in the water mains. And if we've got fresher, newer water, we're going to see a reduction in our disinfection byproduct formation. So there are other benefits to a good flushing program. It gets operators out there. They're looking at the system. They're looking at the hydrants. They're exercising them. They're performing maintenance. And when we do that, we discover if there's problems, and we can fix those. If we just ignore them and we don't do these things, then we don't know if there's a problem, and maybe they won't be available to fight a fire or something like that. We had mentioned flushing. In addition to flushing, there's the concept of flushing velocity and scouring. And so ideally, if we're going to flush our system, we want to get that water velocity up to 2.5 to 5 feet per second. So that's going to help scour things out of the pipes. And you can see here we've got manganese in this pipe. We've got an iron pipe that's got some tuberculation and some slime, and then we've got biofilm on this pipe on the bottom right. So that's all stuff that we would like to get out of the system in order to maintain a higher water quality in the distribution system. And normally water goes through the system pretty slow, and so increasing the velocity is going to break that stuff up and flush it out. Some systems that have issues with this, that routinely have problems with stuff, sediment and things, will end up notifying their customers that they can expect rusty water due to a flushing coming up. And then there's different ways you can flush. One of the best ways, I guess I should say, is unidirectional flushing. And so the idea here is we've got this, and this is a pretty well looped system compared to what we were looking at before. So we want to create higher velocities in there, and that's going to cause that scouring action. And in order to do that, we're going to close up some of these valves, and we're going to make it so that the water has to go in a given path. The thing with looped systems is the water can go wherever it wants to. So we're going to make it go in the direction we want, and we're going to flush that out, and that's going to get us some of our scouring action, and it's going to remove those sediments from the system. And you want to work from either the point of pressure or from the source outward, so that we make sure that we pull all that from the beginning out to the ends of the system. And this figure is here. It demonstrates that it's not, ideally we're looking at 5 feet per second velocity when we do flushing, but there's a point of no return where if we get too many volumes, we're not getting a benefit from that. And so it's important to stick with that, with the flushing volume, and beyond 3 doesn't appear to be all that helpful. So here's this is some example of some other places where we can see contamination that might enter our distribution system. If you've got wells, in this case, the well doesn't have it doesn't have the bolts in the cap. We've got an overflow on a tank that's too close to the ground, potential for things to try and get up in there, or something to be sucked in if there's some sort of drop in pressure in the top. And then we've got a tear in the vent screen, and that could allow bugs and things to get in there, which they get in, they die, they could cause issues with coliforms and things of that nature. The pipe that we have in the system can also have a factor on what the quality of the water is in the system, in the distribution system. So we can have permeation and things like gasoline and chlorinated solvents. If they're in the ground, they can enter the pipe, certain types of pipes, and so that's something we have to be mindful of. We can also have a situation where we've got pipes that leach material from the pipe itself into the drinking water. So that's also a concern. So in 1992, over 100 known permeation and contamination events were studied, and 89% of those were related to gasoline-related products. And here's another example. In 91, a 10-gallon gas tank leaked on the road, which doesn't seem like a lot, but it resulted in benzene and toluene, which are components of gas, levels of those over the MCL as it permeated the PE pipe. So this is here's an incident where they tested the water inside of a pipe after a gasoline permeation incident, and you can see that the results for benzene benzene and toluene were very high. Once again, those benzene, toluene, ethylbenzene, and xylene are all gasoline components. And as we tell, leaching is kind of the other thing where, you know, we've got our pipe, and the pipe itself is somehow making itself into the water. There's a couple links to additional information if you're interested in that. So another potential source of contamination are main breaks and repairs, and you know, it's important that we do the best we can when we're repairing water mains, to not allow contamination to enter into our pipes. You can see the photo on the left. There's quite a bit of water in that, and it looks like they're trying to pump that out so that they can actually make the repair. Well, it's important to be able to make the repair, but it's also important to get that water out of there so that it doesn't impact the water inside the distribution system after we've made the repair. On the top right, we've got water spewing out, and typically if you can maintain a good pressure, then you know, it's going to make the job a lot easier. So if you can repair under pressure, it makes things typically go better, and it's you'll have better results. And then if you do have a situation where you lose pressure, you drop below 20 psi, I would suggest that you issue a boil water notice until you get negative BACT testing confirming that the water is safe. And more so, if you have any of these events and you have any concerns, I recommend that you contact your regulating agency. That could be the state, it could be EPA, depending on who regulates you, and discuss it with them, because they'll have some good advice, and it's important that they're aware of this, especially if you've got a break, or especially if you have loss in pressure and you're issuing a boil water notice. So distribution system protection, the two most important things that we can do is we can maintain positive water pressure. And then we also need to maintain the physical integrity of the system. So as we can see in this little photo here, or diagram, we've got a hole in a water main, and if we have low or negative pressure, this water out here that's contaminated with E. coli can enter into the pipe, and then that can go to off to our customers. Now remember that if we maintain a good free chlorine residual, there is the possibility that the chlorine that we have in the water will be able to react and nullify that E. coli. But if we don't have that, then it's not going to happen. And this is an interesting study from 2017, found that households are almost twice as likely to have acute gastrointestinal illness after a pipe break or a repair in the distribution system. So that just further shows why we should use proper techniques. So we've got a table here that it identifies different water quality issues, and it separates them into what types they are. I think it's important to note that the ones that could affect public health are the most important things, and microbially that could be pathogens, and chemically you could look at, there could be chemical contamination. You could have an exposure to excess chlorine if you chlorinated the pipe after a break and then you didn't flush that out before connecting everything back up and opening your valves. So this table here just shows that this was a study of different main repair sites, and the sampling shows that there was there's total and fecal coliforms and other things that were found in the trench water and the soil around it. So those are definitely, if we've got to break the soil and trench water could be sources of contamination. In 1990, there was an incident, an outbreak of E. coli that resulted in 240 cases of illnesses and 4 deaths, and it was concluded that it was from contamination from 2 major pipe breaks. The operators flushed the pipe after the repair, but they didn't disinfect the repaired main. So what operational practices can we use? We want to make sure we isolate the breaks so we can limit the area that's affected. It's really important when it comes to a boil water. Nobody wants to have more people boiling water than they have to. And we need to flush and we need to disinfect. All right, so we're on to our first poll. How can operators protect water quality when repairing main breaks? A, isolate the repair site using valves. B, flush the line after making the repair. C, disinfect the water main. Or D, all of the above.
All right, the poll is now launched. We'll give everyone just a minute to get their answers in. Go ahead and get your answers in. We'll be closing the poll in just a couple of seconds. All right, closing it now. All right, and we had 98% of people said D, all of the above, which is the correct answer.
Okay, well, 98%, that's great because we will go through, and D, all of the above is the correct answer. Good job. So we will talk about backflow now. A backflow event requires 2 different things for it to occur. So we're going to have a cross connection first, and then we have to have a pressure differential that causes that water to flow from that cross connection into our distribution system. So a cross connection, that's a plumbing arrangement that makes it possible for a non-potable substance to enter the potable drinking water supply. Types of backflow. So here we show back siphonage, or we're talking about back siphonage, and that's a loss of system pressure. It could be a main break. We could have a drain on the system due to fire suppression. We could have an outage. We could have a power outage, and now we're not able to, our pumps don't function. But what it does is it creates a vacuum that draws in that non-potable water. And then we also have a back pressure, and that's where our customer's pressure exceeds the pressure in the system, and it allows that water that the customer has, water, contamination, whatever, chemicals, whatever they are, to then be forced into the public water supply. So both of these are potentials for causing contamination. So this slide is a little more graphic, but in this example, we have the water pressure is reduced because of a break in the water main, and then somebody had this this tap with a hose set up, and they were filling this tank that had chemicals in it, adding water to it. Well, now it's allowed to reverse its flow because there is no pressure pushing against the faucet, and so that allows that to siphon back into the main. And if that happens without backflow prevention, you know, we could have these contaminants entering into the drinking water system and harming public health. So here's a diagram that shows you know, backflow into drinking water from back pressure. In this case, we've got a plant, it's got a chemical pump or a boiler, and that could develop a pressure that exceeds the pressure in the distribution system. And that could result in a backflow due to overpressure. And so if you look here, there's 2 locations that would be recommended to have backflow prevention devices installed. This location here is going to protect the entire distribution system. But putting them in both locations will protect the distribution system, but it's also going to protect, by putting one here, we can protect the people that are on site at this plant and might be drinking out of the water fountain. So they're both important. Obviously, it's most important to have it here. If this was, you know, if there wasn't anybody on that location that was drinking, if they didn't have the ability to drink the water on site, it wouldn't be a concern to have that second one. And here we show some of the different backflow prevention devices. We discuss them and what type of hazard levels. These things are all, we look at them as hazard levels. How bad is the hazard? And we can see how they operate. And so for different applications, we have different types of devices that we recommend. You know, when we look at the photo developing equipment, there's chemicals in there. So, you know, that needs to be a more high, that has to protect against a higher health hazard, as does the boiler. Things like the cafeteria cooking kettle and the dishwasher are typically, they're less hazardous because, you know, hopefully the things that are in those aren't hazardous to human health. But you know, the way this works is the air gap is the best backflow prevention device. However, it doesn't work in pressure situations. So there needs to be, it works well if you're filling a tank and you can have a pipe that drops above the tank, doesn't go below the surface of the tank and drops it in there, but it can't provide any pressure. You can't provide pressure and use those. And so the reduced pressure zone, or RPZ, the double check, and the vacuum breaker, this is, you know, these become less, they prevent less as you go down that list. So now we're already onto our poll 2, which is which backflow prevention device would allow the minimum necessary protection from backflow when providing water under pressure to a chemical facility? A, reduced pressure zone assembly, B, double check valve, C, vacuum breaker, or D, air gap. Understand that your questions might be a little bit different in order to fit them into the system. So.
All right, so we just launched that. Go ahead and get your answers in.
Also, Daryl, just a heads up that for a couple of your slides, the very bottom part was a little bit cut off. So I'm not sure if you're able to zoom out of your slides a little bit, if that might help. But it's just been in like a couple of the slides that it seems like some of the language is a little bit cut off.
Thanks for letting me know. I apologize for that.
No worries. And just a reminder also for everyone, the slides are available in the handouts tab. So if there was anything that was missed on any of the slides, You can just go ahead and open the PDF version of the slides in the handouts tab too. All right, go ahead and get your answers in. We'll be closing the poll in just a couple seconds. All right, closing the poll now. All right, so we had a mix of answers for this one. The majority of people, 36% said A, 29% said B, 14% said C, and 21% said D.
Okay, so it's across the board. So in this situation, obviously an air gap is the best, but we need to be able to provide pressure to the chemical facility. So that's out. We can't use an air gap in this case. And then it is a pretty high hazard. It's one of, a chemical facility is one of the highest we're going to have. So the most protective other than the air gap would be the reduced pressure zone assembly, the RPZ. So answer A would be the correct answer. All right, so now we're going to go on to talk about chlorine disinfection and disinfection byproducts. So I love this slide from the standpoint that it shows some of the benefits that we can see from chlorination. So if we look at this, there were thousands of deaths that used to occur due to waterborne diseases, but nobody understood why they were happening or how it was happening. It wasn't until the 1670s, excuse me, when we could first look at microbes under a microscope. In 1854, John Snow did some interesting stuff, identified that cholera was a cause of a waterborne disease epidemic. So that's John Snow and the Broad Street Pump cholera outbreak in London. It's really interesting. I understand that there's a couple of books out there if anybody's interested in that type of thing. The Strange Case of Broad Street Pump and The Ghost Map are the names of the books that I was able to find, but really interesting what I've read on that. In the 1860s, Louis Pasteur developed a germ theory, and that theory was that microorganisms such as bacteria and viruses are the primary cause of diseases. Until then, they really didn't know. And then in 1908, in New Jersey, they installed the first chlorination system for drinking water. As you can see, so we've got the difference that we from 1908, the blue line, until 1945, we went from, in this case, it appears to be 24 deaths down to 1 death per 100,000 people. So chlorination is important. So disinfectant types. So we'll talk about a couple of different disinfectant types. So we've got chlorine. One of the great things about chlorine is it results in a free residual. So we'll have a residual that will go out in the distribution system, and it can attack those pathogens. It's very reactive. It's the primary disinfectant in water treatment. It's the most common form of treatment, in part because it does provide those that residual. Unfortunately, it can lead to disinfection byproducts. There's also chloramine is another. There's several other ones, but we're going to cover chlorine and chloramine. Chloramine is another one that can be used. And when we look at that, it's the total residual. When we do our testing, it's a more stable type of disinfectant. We make that by combining chlorine and ammonia at a 5-to-1 ratio. It's also often used for secondary disinfection because so that in addition to chlorine. And the good thing about that is it doesn't produce those disinfection byproducts. Unfortunately, nitrification can occur with high water age, and that's converting ammonia to nitrate, and that nitrate can be a bad thing out in the distribution system. This is probably one of my favorite concepts when it comes to this stuff, and it's the concept of breakpoint chlorination. I've talked with a lot of operators over the years about this concept, and it's really a difficult one to get across. So when we look at this, where we've got chlorine residual increasing on the left, and as our chlorine's applied, And so if we look at when we initially apply chlorine, we don't see any chlorine residual resulting. And so that's because there's reducing compounds that take up that chlorine. And then as we add additional chlorine, we start to get a chlorine residual, but we're also forming these chloramines. And the chloramines are the things that cause the odor and taste complaints. And so if we look at this, I would often hear from operators that I don't want to apply any more chlorine because I just get more complaints. So what really, if we follow this curve, what happens is we get to a point where that stops. And then as we apply additionally, we see a reduction in the residual, but we're also gonna destroy most of those chloramines. And so the taste, odor issues, the smell goes away. We hit this break point here, breakpoint chlorination. And at that point, pretty much everything that we apply is available as free chlorine. So it takes us away from the parts that nobody likes and puts it into having something that provides that safety out there in the distribution system without the taste and odors. All right, and this just to show that the stuff that we have until up to breakpoint, the chlorine residual, that's the combined chlorine, and then the free residual is the stuff above that. We add those two together, and that gives us our total residual. All right, so viruses and protozoa are inactivated when we add disinfectants, and that means that they're not able to replicate or reproduce. But when it comes to bacteria, we need to destroy those. So those are both a different. And what the main factors in how effective chlorine disinfection is, it involves the residual concentration, or the amount of chlorine that's available out there, and then it's also how much time that chlorine is in contact with the water, so that it can affect those pathogens. I threw this in here, and I think it's important if people are interested, if they want to know information about how to disinfect water mains, they can go and look up this AWWA standard. But just know that most of these, and there's others, but most of them involve the use of highly chlorinated or highly concentrated chlorine. So there's a link, or that identifies the AWWA standard for disinfecting of storage tanks. And then we've also got the standard listed here for disinfection of wells. I think it's important to note that after disinfection, we have to deal with that chlorinated water. And so that chlorinated water should be dechlorinated, and we should flush it to waste somewhere. If we don't dechlorinate it, it has the potential, if you put it in the sewer, it could kill everything in the sewer, and that could upset the wastewater treatment plant. So there's several different reasons why we would want to, we're applying this chlorine, and we want to monitor what our residuals are out in the distribution system. And one of those is that there's a maximum residual disinfectant level for chlorine of 4 parts per million. So we can't go over that. And then we also have minimum recommended residuals of 0.2 parts per million for chlorine and 0.5 part per million for chloramine. By monitoring the chlorine residuals, we can ensure that we've got what we need out there in order to work against those pathogens. We can also, hopefully, we'll stop or slow or remove the biofilm growth in pipes. And then if we did have if we noted that we're using more, our residuals are lower than normal, that could indicate that there's a contamination issue out there, there's a problem. So that gives us good information. And then also just to make sure that we have enough chlorine residual out there, especially in those remote sections or our dead ends. Here we have, this was from a study where they looked at the chlorine residuals over time, and it's typically the things that cause that are going to be the temperature and any demand out in the system. Normally, the residuals in a distribution system should last a few days up to a few weeks. But as we can see from this example, we're trying to maintain a 0.2 out there. this study had rapid chlorine decay in a distribution system, a matter of a week or so, and you might be down to that point too. And you can improve that situation by flushing sediments from the pipes and making sure you've got those scouring velocities up. We can clean our storage tanks, and cast iron pipes are it's not a great water main material by current standards. So if we can replace that or line it, that can help with it as well. We can reduce our water age by flushing those dead ends and making sure that we've got turnover in our tanks. So we talk about disinfection byproducts. There's two different main groups of byproducts here. We've got the total trihalomethanes, and so these are four volatile organic compounds. They can be found in drinking water when we add chlorine, and they're regulated because they could pose a cancer risk if we find them in the distribution system over 0.08 parts per million. They're formed by a reaction with the naturally occurring organic matter that's in the water, and then we add the chlorine. Those two things react. And haloacetic acids are that's the other group, the HA5s. They're these 5 weak acids, and they also there's concerns about cancer if they're at 60 parts per billion or more for the MCL. Both of those are formed during those reactions with the naturally occurring organic matter and the chlorine. So how do we prevent those in our distribution system? So we can add mixing to storage tanks if we've got an issue with our storage tank. We can ensure that we've got tank turnover of 5 days or less. We could use chloramines as our disinfectant, and that would limit the amount of the production of disinfection byproducts. We can also flush our dead ends in those areas where the water tends to sit, and we can clean our tanks and flush our mains to remove that debris. So we had mentioned that chloramines potentially cause nitrification. Well, what are the impacts of nitrification? So we've got the high nitrate levels, and nitrate's not a good thing to have in the water. We could have a loss in our disinfection residual. We could grow bacteria in the system. And what leads to nitrification? So once again, if we're using chloramines, we have the potential to form nitrification happen. If we've got ammonia, it can be a food source for bacteria. We've got warmer temperatures and a lack of sunlight that can affect and lead to nitrification. If there's sediments in our distribution system, they can harbor bacteria, which can lead to it. And if we've got a significant drop in our pH and our alkalinity, that can affect nitrification. And nitrification is a microbial process where ammonia oxidizing bacteria convert ammonia to nitrate, which is then oxidized to nitrate by nitrate oxidizing bacteria, and that's where the bacteria come into play. So our solutions increase our disinfection residual, mix our tank, cycle our tank, and keep the tank clean. So disinfection and biofilm study findings. So there's been some studies that have been done looking at disinfection and how biofilm reacts to it. And they found that if we initially apply free chlorine and we follow that with chloramines, that's an effective disinfection strategy to reduce those biofilms. And then also if we follow up disinfection, flushing followed by disinfection is also an effective sequence. So that high velocity flushing removes that biofilm layer, and it allows that disinfectant to get down into the biofilm. And one thing I'd like to warn everybody about, if you're considering changing your disinfection strategy, you need to make sure that it's going to work. You need to investigate it, look at it, you need to pilot test it. And in a lot of cases, it could require permit to change your disinfection process by your regulating agency. All right, so this is a portion of the table from the disinfection byproduct rule quick reference guide from EPA. One of the things I want to note is that compliance is based on the locational running annual average. So you're going to have, if you've got 4 sets of samples in your distribution system, and say you're required to collect, so you'd be required to collect those quarterly, it's going to be a comparison of the last 4 results. They're going to average those, but it's going to be per location. So each one of those locations is separate and needs to meet that MCL in and of itself. And as we've said, those disinfection byproducts form when chlorine reacts with organic compounds in the water. Now there's a couple things, other things on this table. There's an MCL for bromate, and that's comes up when you've got systems that use ozone and have bromide in the water. So then if you're adding or using ozone as a disinfectant or in the process, then you would have to test for bromide in the water. And then if you're using chlorine dioxide as a disinfectant, then you're going to have to test for chlorite, and there's MCL for that as well. So remember, we've got these MCLs. They're based off of locational running annual averages. These show that we've got 80 parts per million and 60 parts per million respectively for those 2 sets of chemicals. And the initial distribution system evaluation is a study that would have to be done typically when this rule went into effect, or if a new system comes online, and that's to identify, the idea is that we want to identify the most likely locations for these disinfection byproducts to form. Where are we most likely to find them? And so we're trying to look at, worst case situations, and that usually happens in those long retention time areas. Could be dead ends, areas where the water doesn't flow, there's not a lot of use. And also we tend to see that the results are higher at the warmest times of the year. Those byproducts form more in warm water. So these are just some information that you can look at. Just goes through the different type, what to expect when in conducting the sampling, what kind of bottles are used. So now we're on to poll number 3. What are factors that can lead to increased DBP, disinfection byproduct production, and loss of chlorine residual? A, tank turnover less than 5 days and excessive flushing. B, tank turnover greater than 5 days and sediment buildup. C, use of chloramines and system flushing, or D, all of the above.
All right, so I just launched that. We'll give you a little bit to get your answers in. All right, we'll give everybody just a couple more seconds, and then we're going to close the poll. Okay.
Okay.
It looks like most people, 75% of people, answered letter B.
Okay, thank you, Zoe. Yeah, so letter B is the correct answer. And that's, if we look at A, tank turnover less than 5 days and excessive flushing, those would all reduce our DBP production. Use of chlorine, C, use of chloramines and system flushing. System flushing reduces DBP production, and chloramines don't create DBPs. So yeah, it would be tank turnover greater than 5 days, which is not a good thing. And then having sediment built up is also not going to be a good thing. So, all right, so The last few slides, we're gonna cover some of the important aspects that are associated, are affected by conditions in the distribution system. So the total coliform rule is important for operators of distribution systems because you have to collect your samples. And two of the most important aspects of that are the repeat sampling requirements and the number of samples that are required. It's based off the population. So there's a quick reference guide to EPA listed at the bottom. So if you have a positive sample, if it tests positive, that means you have to collect at least 3 repeat samples within 24 hours at the following locations. So you're gonna have to collect the original routine site, you're gonna have to collect within 5 service connections upstream and within 5 service connections downstream. And so, and then if you're a small system, so if you collect 1 routine sample per month, that means that you're gonna have to collect a 4th sample out in the distribution system that's representative of the distribution system. Remember that the number of samples is based off the population. We'll see that in the next screen. And then it's notable that systems that serve 4,900 people or fewer, they can collect all their samples for the month on the same day. But if you have a population higher than that, then you need to separate those samples out throughout the month. And this is from an EPA reference guide, and you see just the populations and how the sampling required minimum samples per month are laid out. So here's an example of a sample siting plan. And as we said, they have to be at representative points throughout the distribution system. That sampling plan identifies those routine locations. And it also identifies what repeat locations you're going to use that are within 5 upstream and downstream of the original location. And then some of the important concepts associated with that is, you need to look at different population centers so that everybody's represented. You want to look at different pressure zones because it could easily be different water in different pressure zones. We want to have different geographic portions of this distribution system. If we've got an area that's considerably far away from the rest of the system, you might want to sample there. And then if you've got different sources, and by different sources, what I'm getting at is that quite often well systems have several wells throughout the system, and then you need to try and get some water from each of those different well systems. So here we're going to go over and just show what we mean by the sites that we're going to use. We can see that our routine site is 1, 2, 3. We've got repeat sites at 100 and 189. And so our downstream site is 189, and that's 1, 2, 3, 4. That's the 4th or the 5th location downstream, so that's good. And then if we look at 100, it's the 5th location as well, so that's good. So when you come up with these plans, you want to make sure that you have access to those upstream sites as well as the routine site, upstream and downstream as well as the routine. And then the lead and copper rule, that's out in the distribution system. It can be affected as well by the water quality in the system. And so the federal rules call for a 15 parts per billion as an action level for lead and 1.3 parts per million as the action level for copper. It's funny because Michigan has actually adopted 12 parts per billion for lead. So they're a little more strict on those than the federal. Some other states are doing a little bit more little things with service line removals being more strict as well. And that's based off the 90th percentile level of the tap water samples. 90th percentile would be the 9th highest out of 10 samples, for instance. The samples have to be a first draw from a tap that hasn't been used in the last 6 hours. The standard sampling frequency is 6 months. It can be more restrictive. You can have to do it more often, or they can reduce the schedule based off of favorable results over a certain amount of time. That'd probably be up to your regulating agency. And so if you've got an AL exceedance, an action level exceedance, it can trigger other things. It's not a violation in and of itself. You may have to do additional water quality parameter monitoring, corrosion control, treatment study, monitor your source water or your treatment, provide public education. And if you've got lead service lines, I imagine you're going to be replacing them regardless of whether you have, at some point, regardless of whether you have an action level exceedance. Here's some links to some of the different guides. And as we showed with the coliform sampling, there's a table established, and it indicates based off of population or system size what the standard and reduced number of sample sites and water quality parameter tab sample sites are. In order to select these locations, you want to first look at tier 1 sites, which are single family, so single family homes that have copper with lead solder. So they were constructed between 83 and 88, or if they have lead pipes, obviously with either goosenecks, pigtails, or they have lead service lines. The next tier is tier 2, and that's going to be, they're going to extend that out into all the building types. So it's not just single family. We're going to try and collect all those other ones that have the same characteristics, but they might be multifamily rather than just being single family. And then if you don't have those, we need to do this. We try to collect all our samples from tier 1. If we don't have tier 1, we supplement with tier 2. If we don't have tier 2, we supplement with tier 3. And those basically are single family. We go back to single family with lead solder constructed before 1983. And then it's an all other. So we're using whatever samples are available. If we don't have enough 1, 2, or 3, then we would go to the other. So now we're on to our poll number 4. What factor needs to be taken into consideration when selecting routine total coliform sample locations in the distribution system? A, availability of repeat sites within 5 locations upstream and downstream. B, different pressure zones. C, different water sources. Or A, all of the above.
All right, so we have that launched. Let's get our answers in. All right, just a couple more seconds before we close the poll. All right, it looks like the majority of people picked D, all of the above.
All right, well, that's good. Thank you, Zoe, because that is the correct answer. So, you know, we can't come up with locations and if we can't get upstream and downstream sites. So we need to make sure we've got those in case we need to do repeats. We discussed the need for different pressure zones and also to take into consideration different water sources. So yeah, all of the above is the correct answer. Okay, so what are our main takeaways? 3 things that we like you to leave with. Water age management and flushing. It's most effective when we've got a velocity of 5 feet per second and we put through 3 pipe volumes. And it's part of our water main repair procedures, water age control, and biofilm management to improve water quality. One of my favorite things to talk about is breakpoint chlorination. Requires the application of enough chlorine to destroy the chloramines and allow for additional chlorine added to be free chlorine available to kill those pathogens. And then cross-connection control involves protecting public health by ensuring adequate separation or isolation between contaminants and drinking water. All right. So I don't know, we've got, I ran a little bit longer than I wanted to. A lot of stuff to cover here, but if you think of it and you want to share something in chat that you liked about the presentation, but I'm available to answer any questions if there are any, we have any, and we have time. I'd also like to say that if you're, once again, if you're interested in the 5-hour session of this, the expanded version, please sign up to take that. It's January 6th and 7th, I believe.
Awesome. Thank you so much, Daryl. So yes, and we did drop the link in the chat to register for that event that Daryl is referencing. We did have quite a few questions come in. but I know that we are at time right now, so maybe we can just get through one or two together.
Sure.
And Daryl, I also am going to send you a document that will have all of these questions in, if you don't mind answering those. And that way, whenever we send a follow-up email out to everyone, they can get their questions answered if they have to go ahead and hop off right now.
Sure. I'd be happy to do that.
All right, so first question is there any key criteria like depth or ratio, et cetera, that will predict water will short circuit in a storage tank?
Yeah, well, you could look at, there's a lot of it is just looking at the design, you know, where the inlet is, where the outlet is. I've had situations where I required that the inlet pipe be directed in the opposite direction of the outlet pipe, so that it went in and it forced the water in that tank to go all the way around before it came out. So there's different things that you can look at, and it usually becomes apparent. You know, a lot of it has to do with where that inlet and outlet pipe are. Are there any baffles in the tank? Because baffles, you know, there'd be structures in between that force the water to go in different directions. That can also help with how long that water is going to stay in the tank.
Wonderful, thank you. And we'll just go through one more question, since I'm sure you're a busy person and you've got some other things to do. But someone had said, you mentioned negative pressure. I never had a firm understanding of what this means. By definition, LOPP would be 0 PSI or less. I think you said 25. Is there any standard on what the PSI would be to equal loss of positive pressure?
So any pressure below 0 is going to be a loss of positive pressure. We try to operate at greater than 20 PSI, because at that point there's not a lot of safety factor in our in what we have for pressure. So loss of pressure, true loss of pressure, is going to be below 0. And what happens with that is it you know, it back siphons, it pulls the water leaving the water main is going to pull water with it. So if you had a loss of pressure, it would, you know, for instance, if you had a 2-story home, it's going to pull all the water out of your home plumbing. As that water leaves the water main, it's going to pull it all with it. So the same concept is if you had an open connection to a source of contamination. If you didn't have you know, if you had that open, you're pumping water, putting water from your hose into a pan. If the water pressure goes to goes below 0, then the water will eventually go someplace, pull out of the main, and then pull that water in. I hope that's helpful.
Absolutely. Thank you so much, Daryl. All right. Well, a huge thank you to you, Daryl, for sharing your expertise with us today. And following this webinar, each of you will receive a follow-up email with the slides from today, as well as a link to the recording of this webinar. And then any of those questions that we didn't get to go through today, we'll have Daryl answer, and we'll share those in the follow-up email as well. We ask that you please complete the webinar evaluation so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics that are important to you. Thank you again, and we hope to see you all at future EFCN events. Thank you, Daryl.
Thank you.